But for today, we'll talk about the Kalman filter. It is hard to overestimate or overpraise the importance of the Kalman filter. I said it last week. It has been used. It has been an essential element in making a human spaceflight possible. So to precisely estimate the trajectories of the Saturn rockets and so on, and of satellites that we've sent up. It is used all across the bar. So you will find it in the high energy physics when you try and track particles and detectors. You will find applications in finance. You'll find applications in biology. You'll find plenty of applications in military. So it's used all across the board. So the Kalman filter, it's a state space model, just like the hidden Markov model, which we talked about last time, which is why it's a logical extension or logical continuation, except we will see that the hidden state is continuous, not discrete. It's in the hidden Markov model. So that will be the main topic of today. But before we start with that, we need some basics. And for now, I want to start here with the sequential Bayesian estimation for the normal distribution. So what I mean by that, I'm interested in finding out what is the probability of z given x. We know from Bayes' theorem, this is probability of x given z times p of z. And I'm interested today in the case where this prior is a normal distribution and this likelihood is a normal distribution. And if you multiply a normal distribution with a normal distribution, you know that you also get out a normal distribution. And we're interested in the parameters of this posterior. Yeah? So we need names for these parameters. So I will say that this prior here has a mean mu z and covariance sigma z minus 1. And the likelihood of a measurement x given z is also given by a normal distribution which is centered on z with a covariance of sigma, I'm writing here x given z to the minus 1. All right, and I was just saying that we then also get out a normal distribution. And by the way, if so I'm writing down names again. This is prior, this is likelihood, this is posterior. And if the prior and the posterior are in the same family, then we call that prior a conjugate prior. So this one and this one are the member of the same family. Family in general can be a bigger family, like, but here, this is actually a normal distribution that we get out. So member of the same family, so we call this a conjugate prior. All right. Now, let me start with a sketch here in one dimension. I'm going to use different colors. Let's say my prior is blue. So I'm claiming that this here reflects my prior assumption of what is the true value of z. And then let's say we have some measurement. And let's say that our measurement is actually, it has pretty poor accuracy. So let's say this is a very broad Gaussian here. This would be my measurement. And now we want to find out the posterior. So I'm mixing blue and red here, so I'm using purple for the posterior. So we know it's a normal distribution. So we need to specify its mean and its spread. So the mean, the mean of the prior was here, the mean of my measurement was there. So I guess it's fair to assume that the mean will be somewhere in between the blue mean and the red mean, right? We have some prior, we update it with some measurement. So we would guess that the new mean is somewhere in between. What do you think? Closer to the blue or closer to the red mean in this case? Yeah. The red mean has a high spread. The blue mean has a smaller spread, or the inverse of the spread or inverse of the variance. We also call this the precision. Yeah, so in one dimension, we would say that here the variance is sigma squared, and this would be the variance. And here, this variance is relatively small, and this one is relatively large. And then there is something that we call the precision. So it's just the inverse, yeah? 1 over sigma squared. So the precision here would be relatively large, and this one would be small. So you have argued that the new mean is probably closer to the blue one than to the red one. And I think we can all agree with that. Now maybe a trickier question is, what do we expect the spread of this new distribution to be? So is it also compromise between the blue and the red one? Or what else? And I'm not going to directly ask you now, because I think the intuition that some people have might be misleading. So we will see that, like you said, the mean is going to be closer to the blue one than to the red one. So let's say the new mean is here. And actually, its spread is going to be smaller than either. So its precision is going to be higher than, and it's not a nice Gaussian, but you know what I'm getting to. So I'm claiming that that the spread of the posterior is going to be smaller than either. And let's confirm this in formula. Okay. So I need a bit of space here. All right. So we will just write down the formula explicitly. And because I don't want to deal with the exp all of the time, I'm going to take the natural logarithm. I'm going to multiply with -2. P of z given x. I don't care about the denominator, and I don't care about the normalization factors at this point. So I'm writing this as a constant plus. And now we said that one term was the likelihood. Let me make in this likelihood here a tiny modification. Namely, if we have an unbiased measurement, then probability of x given z is centered on z. But we will later need a linear transformation, and so I'm multiplying my vector z with the matrix C here. Okay, so C is a matrix, and we don't need it for the picture, or you can for the time being just imagine this capital C to be the identity matrix, but we will need it in the Kalman filter later, and so I want to introduce it now. Okay, good. So then this first normal distribution here when we take the negative logarithm, multiply by 2, we get x minus c times z transpose. And by the way, I made another mistake in my notation here, because normally in the covariance matrix, or when we specify the normal distribution, we give the covariance matrix and not the precision matrix. So I'm deleting the minus ones that you see here. Okay, apologies. But now I need the minus 1. All right, this is the first one. And now the second normal distribution, this one here, we will have z minus mu z transpose sigma z to the minus 1 and z minus mu z transpose. Good. And now we want to get this posterior. And I'm going to give some dummy names to these parameters here. I'm going to say that this is going to be distributed about mu z given x, and that this will have a covariance sigma z given x. All right, so that means I want all of the above. I want this to be the same as what I'm expecting on the left-hand side. On the left-hand side, I'm expecting z minus mu z given x transpose, and sigma z given x to the minus 1, and z minus mu of z given x. All right, so I want the first line to match the second line, and we need to find the unknowns here, the mu and the sigma. And as we did when we were talking about Gaussian processes, we will achieve that by comparing coefficients. Okay, so first, to obtain this sigma z given x, we will first find all terms that are quadratic in z. So if I'm looking at this first equation here and the terms that are quadratic in z, then we have z transposed, c transposed, sigma x given z to the minus 1 times cz. And we had from the second term, we have z transposed sigma z to the minus 1 z. So altogether, I can say this is c transpose sigma x given z to the minus 1 c, c, and then plus sigma z to the minus 1 times z. Good, and this should be the same as z transposed sigma z given x to the minus 1 z. And so by just comparing the left and the right-hand side, we find that this sigma of z given x is the following: c transposed sigma x given z minus 1 times z plus sigma z minus 1 to the minus 1. Okay, it's very much the same thing as we did when we were discussing the Gaussian processes. So we found the covariance, and interestingly, this here was the precision of the prior. This here was the precision of my measurement, or of the likelihood term. And we see that these precisions add up. So in our one-dimensional example here, this confirms that if I take the blue distribution as prior, the red distribution as likelihood, then I get a posterior here, which is purple. And this purple distribution indeed has a smaller spread than either. Yeah, the precisions have been adding up. So even a poor measurement, or a measurement, let's say, with a great uncertainty, even such a measurement will always increase my overall precision or overall certainty in my estimate. And by the way, if we do something simple, like just computing the mean of a random distributed random variable, then you all know the formula that the mean is 1 over n, is just the center of mass. And you also know that the spread decreases as 1 over n. But we could also do this sequentially, by adding always one observation at a time to our estimate and keep updating our estimate. And our mean eventually will go to the center of mass, and our spread will diminish over time. Our precision will increase. All right, so we have found at this point the covariance matrix of the posterior, and we still need the mean of the posterior. So secondly, to obtain mu of c given x, we now find all terms that are linear in z. So I'm copying from the equation that you see at the very top of the screen. So this will be minus twice z transpose of c times sigma x given z to the minus 1 times x plus sigma z to the minus 1 times mu z. And we want this to be the same as the linear term in our posterior, which should be minus twice z transpose sigma z given x to the minus 1 times mu of z given x. All right. So this thing here, this is wanted. And from this equation, we can see that mu z given x is sigma z given x times c times sigma of x given z to the minus 1 times x plus sigma z to the minus 1 mu z. And I want to write this result in a slightly different form. I want to write it like this. I want to say this is c times sigma x given z minus 1 divided by this precision matrix, the precision of the posterior, which was I've been losing a couple of transposes on the c's here, I think. Yep. So it's this much times x plus okay, times yz. All right, let's look at this. We have here the mean of the prior. We here have the new observation, or the new measurement. And up here we have the precision of the prior. And down here we have the sum of the precisions of prior and likelihood. Similarly here, we have the, I'm ignoring this linear transformation here, we have the precision of the likelihood. And down here, we have the sum of the precisions. So in words, what we find is that our new mean the new mean, or the posterior mean, that's more technically correct, the posterior mean is a weighted combination of the prior mean and the observation. And the weights in this combination are given by the relative precision. So I divide the precision of this term by the sum of the precisions. It is maybe even more intuitive. Okay, now you know I've here written this fraction, and one doesn't do that with matrices, of course. Yeah? So so what I mean when I say that if I divide a matrix D by a matrix E, what I mean is e to the minus 1 times D. Okay. So the equation is maybe even more intuitive, you know, if we forget about the linear transformation, and if we just do this in a univariate case rather than this bivariate case. then in 1D we would have the sigma of our measurement. This precision divided by the sum of the precisions times x plus a similar term for the second one. Okay? Good. That was the hard work. I here have a 2D example for you. Now I've parameterized these more or less randomly. We have a, let's say, a blue prior and a red likelihood. This would be my prior. This would be my likelihood. The figures in the public document. And then we get in purple the thing that you see in the middle here. This would be our posterior. And I've constructed this 2D example to show the following. If we did not take the covariance matrices into account, if this is our prior and this is our observation, then we would normally expect our updated estimate to be somewhere in the middle of these, right? But because we have these covariance matrices, it turns out that actually the posterior is not somewhere on the connecting line, but rather the posterior has a mean up there. So if our likelihood and if our prior had identical covariance matrices, then indeed the posterior mean would have been on the line segment between them. But in a more general case, the posterior can be elsewhere. So you can imagine this, for example, as having some, let's say, antenna that has which has a good sensitivity, or let's say a good accuracy in measuring distance along this direction, but it has a poor precision along that direction. But luckily we have a second antenna with a complementary precision, good in that direction, poor in that direction, and given this prior, given this particular measurement, that would be the posterior that we find. That would be our best guess of where the target really is. All right, any questions so far? So what have we done? We were just interested in if this is normal, if this is normal, what are going to be the parameters of the posterior. We've found them by matching coefficients, and we've seen examples in this case in a 2D example. Any questions? Yeah?
So the location in this plot would be Z.
So in this plot here, these two axes would, for example, be location. And we are making a distinction here. Let's say this is location, whatever, dimension 1 and dimension 2. And Z would be the unknown location that we want to determine, and we have a prior estimate based on maybe past measurements, and we have our current measurement x with some accuracy, and we want to now get the best possible compromise between my prior expectation and the observation that I've made.
And so the red one is really that px given z.
Exactly, yes.
So I know what the measurement x is, and I plot how likely is that one given each location in that one. That's how the red is.
So the prior here was p of z, and the red one was p of x given z. So we've made some measurement, namely we have made this measurement here, and now the likelihood asks how plausible is this measurement given different possible values for z. And this how plausible, this is shown by this Gaussian, because at this point we don't know the true z. And then we combine the two to get our new best possible estimate, our posterior estimate, which is shown in the bottom plot. Okay, so that was half the math that we needed for the Kalman filter, and actually the second half of math we will not, write down by hand because it would be too much, but we'll look at the concept. So we now come to the Kalman filter. The Kalman filter is another name for posterior inference in a linear Gaussian state space model. And from these words, we can actually, infer everything. Yeah? So first, I'm reading here state space model. State space model. Whenever you hear state space model, you think of our picture. Which looks like this. Where we have a hidden or latent state in the top row. Latent or hidden state or variable. And we also have observable variables. And these observable variables, they could all be observed, but they need not necessarily all be observed. All right, and I'm calling these state space variables here Z1, Z2, and so on. And the observations here I'm going to call X1, X2, X3, and so on. So this is state space model. Now we've also read linear. Linear means that ZT should be a linear function of ZT minus 1. And the observations. So today I will try and distinguish the Z's from the T's. Yeah, the first here is a Z, and the second one is a T. Maybe I should do it. Maybe I should try and do the T like this, but it looks like the A. Ah, gosh. All right. So the subscripts here is T for time, and Z is the variable. All right. The observation at time t is also a linear function of the hidden state at time t. And now we want to make the whole thing Gaussian. So to make the whole thing, to make all of these terms normally distributed, we will actually add a noise term here, where Wt is normally distributed around 0 with a covariance of gamma. And we will also add a Gaussian observation noise Vt, where this Vt is also distributed around 0 with a covariance of sigma. Now, in principle, we could use a different noise at each time instant. So in principle, I could add subscripts t here, but I'm not doing it. I'm here to simplify notation. I'm assuming that these noise terms, that this noise is identically distributed over time. We also need a starting condition. So Z1 is mu0 plus some noise u, where u also follows the normal distribution. All right, so it's a state space model, it is linear, and because all the terms here are Gaussian and because all the transformations are linear, if we transform a Gaussian linearly, we get a Gaussian, so everything is Gaussian. And we're happy. Now let's look at these equations here a little bit. This one here is the deterministic equation describing how my hidden state evolves over time. This is called the model or the state evolution. And well, zt minus 1 is a random variable, but the way in which we transform it is fully deterministic. But then on top of that, we add this innovation noise or model noise. And this noise term is important to account for the deficiencies of our model. Maybe our model does not comprise, maybe our model is not a perfect model of reality. And so we need to give it a little bit of a leeway, a little bit of space. And this innovation noise is a useful way of introducing that. So we have the state evolution, and we have here the measurement process. That tells us how my observation is related to the hidden state. And typically this observation is also fraught by some noise process. This is the measurement noise here. I'm trying hard. Good. All right, these are the basic equations. And now, given our observations, we want to get the best possible estimate that we can for our hidden variables. And there are two fundamental ways of doing this. there is filtering and smoothing, just as with a hidden Markov model. So when we say filtering, then we are interested in a particular hidden state, let's say ZT, given all measurements up to this point in time. And when we say smoothing, then we're interested in ZT given all observations from the first until the very last. So of course, this smoothing is only possible offline. So we have recorded a couple of measurements, and then after the fact, after our satellite unfortunately, crashed to Earth, we can figure out where was it in between. This thing here is online. It says, okay, given the measurements from our radar station, where is our satellite currently? And then I can infer, and what control signals should I now send to make sure it ends up in its correct trajectory. And today, when we say Kalman filtering, we will look at this online scenario. The offline scenario is also important, but it's, well, slightly more complicated. Good. So these are the basic model assumptions of how our observations have been generated. And we'll now have a break. And after the break, we'll look at first a concrete example of what such a model state evolution can look like for something like a rocket. And then we will look at the actual inference. For now, we have a break.